Hello, I'm Rob van der Goot, and today I will be presenting our paper titled Lexical Normalization for code-switched data and its effect on POS-tagging. This is joint work with Özlem Saytinoglu. On social media, it's quite common to use non-standard words, like in the example on the slide. And this might hinder our NLP systems because they have not seen these non-standard words before and don't know how to process them. One way to overcome this problem is to use lexical normalization, in which we translate these non-standard words to their standardized form. In this example, the word PPL is translated to people and the character R is translated to R. And this shows that there is a variety of types of replacements that fall within the scope of this task, where R is more pronunciation-based, whereas for people, the vowels are simply removed. Another phenomena that's common on social media is to use code switching. And code switching is using multiple languages within the same utterance. In this slide, we have two examples from the datasets that we use in this work, where the first one is Indonesian-English and the second one is Turkish-German. Now, if we would normalize these sentences or utterances, we would get the following gold annotation. And as you can see, we need normalizations in all of the languages. So our normalization model needs to handle multiple languages simultaneously. We can also see that because the task is lexical normalization, we might still end up with some ungrammatical subphrases, like for example, till die at the end of the first sentence. We do not include insertion and deletion within the scope of this task. Furthermore, we see in the second example that the third word is actually split into two words. So splitting and merging is within the scope of this task in our datasets. Furthermore, we see that capitalization is corrected in the second sentence. So this simply depends on the annotation guidelines and on the dataset annotation. This is a summary of the two datasets that we use. You can see that both of the datasets are relatively small. The Indonesian-English dataset is about 18,000 and the Turkish-German about 13,000 words, which is why we took apart 20% for testing purposes and used tenfold cross-validation on the remaining 80%. Then the percentage of normalized words is relatively high, 14 and 26%, whereas the percentage of splits and merges are quite small. This is because they are quite peculiar cases of normalization replacements. Then the code mixing index is 28 and 22, and the code mixing index represents the average amount of words that make up the minority language within a sentence. So this means that there is a quite high amount of code switches within our data. For the Turkish-German dataset, there was no lexical normalization annotation layer available. So we took the data from a paper from 2016, and as a contribution, we provide an aligned normalization layer. So it's aligned on the word level, which is useful for training the model. We also provide an alignment of the existing language labels in part-of-speech tags, which can be used for analysis purposes. Existing work on lexical normalization can be broadly divided into these four approaches, where the first one is rule-based, which is relatively common compared to other NLP tasks, because in many cases there is no training data available for a specific language or for a language pair. Then there are the traditional approaches, which are based on traditional spelling correction frameworks. There are also neural network approaches, which mostly use sequence-to-sequence models, and more recently, BERT-based models have been proposed. In our work, we will use MoNoise, which is a traditional model based on the spelling correction framework. We use it because it's state-of-the-art for many languages, and it's especially powerful in low-resource scenarios because it heavily depends on the raw data. And in our case, we have little training data, so this fits our needs well. Furthermore, it's open source, so we can adapt it. In the MoNoise model, the MoNoise model generates candidates for all input words, so it skips the error detection step. It generates these candidates based on multiple modules, and then for each candidate, it will generate a number of features, and it will use these features to predict whether a candidate is the correct normalization or not. And then it will use the confidence of the candidates, the confidence that the candidates are the correct normalization to rank them and pick the best normalization model. You can visualize it as this. So we have an input word, we have a number of feature extractors and candidate generators, which we pass it through. And then we will combine all of these in a random forest classifier, which will predict the confidence score for each candidate, whether it's the correct normalization or not. In this work, we split up our feature generators and feature extractors into two separate groups, where one of them is language specific and the other one is language agnostic. This is not done in the original work, but in this paper we will use these different types of features in different ways. So that's important. It's an important distinction here. So language-specific features can include, for example, word embedding distance, but to the original word, but also unigram probabilities and bigram probabilities. Whereas language-agnostic features could, for example, be this word is the string of this word is exactly the same as the original word, or this word consists only of punctuation characters. The first adaptation we provide is a fragment-based monoise. And the fragment-based monoise just takes the input, uses the predicted language labels from the language classifier to split this input into monolingual subphrases. And for these monolingual subphrases, we practically run two different versions of monoise. So we train one Turkish model and one German model, for example. And then in this Turkish model, we only feed it the Turkish subphrases, and the German model we feed the German subphrases. Then at the end, we glue these back together to get the original, to get the same order as the original utterance and have the normalized version. So some downsides of this model is that we are dependent on the language classifier, and we need to train two different random forest classifiers, which is of course more expensive as training only one. To circumvent some of these problems, we propose a multilingual monoise. And for a multilingual monoise, we generate all the features for all the words. So this means if we have a word in Turkish, we will also generate the German features. So the advantage here is that we don't need a language classifier, and we only have one random forest classifier. The disadvantage is, of course, that the number of features is increasing, which makes also the modeling less efficient, but also more difficult. Then we also propose a language-aware monoise. In the language-aware monoise, we try to circumvent this larger feature space by only generating features for the language of the current word. So this means that in this model, the word embedding distance to the original word will only be used once. And if the word is Turkish, it will find this in the Turkish word embeddings. And if the word is German, it will find this in the German word embeddings. Similar, for example, for the unigram probabilities. So there's only one feature describing the unigram probability. And this can be based either on a Turkish or on a German dataset. To put our results into perspective, we provide scores from two baselines. The first one is the leave as is baseline, which simply returns the input words. And the second one is the most frequent replacement baseline, which returns the most frequent normalization for each word based on the training data. The metric we use is word level accuracy, including also the words that don't need normalization. These are our main results. So let's go through them row by row. The leave as is baseline shows that there's a large amount of words that need normalization, 73 and 74%. Then the most frequent replacement baseline shows that the Indonesian-English dataset is relatively easy compared to the Turkish-German dataset, because many of the normalization replacements are just very frequent. So the score increases quite a bit. Then the monolingual models already outperform the most frequent replacement baseline. It doesn't matter a lot whether you train on Turkish or on Indonesian or on German or on English. On Turkish or German or Indonesian or English. But the differences are significant compared to the most frequent replacement baseline. Then, if you look at our proposed models, we can see that the differences for Indonesian English are relatively small. And this also has to do with the fact that in the Indonesian English dataset, there are many very frequent replacements, which are easy to find. And then the leftover 5% are very difficult to find. So all the differences in the table are relatively small. For the Turkish-German dataset, however, we see some significant improvements. So already when we use the fragments-based model, we significantly improve upon the monolingual baselines. But also the other models improve significantly over the monolingual baselines. And the multilingual model, as well as the language-aware model, is significantly better as the fragments model. Then we were interested to see if we can improve on the downstream task, namely part-of-speech tagging. For this, we use Matchamp, a multitask-based NLP toolkit, which we train on the UD datasets of German and Turkish, and here we use standard datasets, so we can see how we can transfer to a new domain using lexical normalization. We compare this to not using any normalization, as well as using the gold normalization, so the human annotated normalization. These are the results on our test data. So first, we have the leave as is baseline, which here practically means we just return the raw input as they were scraped from the social media. Then the part-of-speech tagger scores 60%. If you use the monolingual monoise models, we already see a huge gain up to 63.47%. But our proposed models gain even further. 64 and 63.92, which are both significant improvements. But we can also see that if you compare this to the gold, the manually annotated normalization, there's still quite a big gap to close. So this leads to the conclusion that the cases that are difficult for normalization have a very large effect on the performance, which means that the cases that are difficult for normalization are also the cases that are problematic for the part-of-speech tagger. We provide a much more in-depth analysis in the paper, which I will shortly summarize now. First, we saw that we got a larger increase in precision as opposed to recall, which is arguably desirable because we don't want to over-normalize. Furthermore, we saw for the language-aware model, the performance of the language classifier is very important. And we saw the largest gains on the German and on the English word as opposed to the Turkish and the Indonesian words. This could be because they are more high resource, but also perhaps because the original monoise was developed on English and other Western European languages. In the paper, we provide more qualitative analysis as well as part-of-speech confusion matrices. Thanks for your attention. Our code and data is publicly available, and these are the references I've used in this presentation.